Hello, and thanks for joining me in this little seminar. I want to speak about the relationship between mixing entropy and sustainable metallurgy. We have nowadays many products that are becoming increasingly more chemically mixed. You see here three typical product groups, for instance, solar cells, windmills, or electrical vehicles. And they are all characterized by the fact that we are using a large fraction of the periodic table to produce them. The same applies to electronic instruments, as you see here from the development from an ordinary telephone through a cell phone and a laptop, which in part can contain more than 45 different elements. This is reflected nowadays by the types of scrap. We have here an example for iron scrap that is used intensely, of course, to make steel, today already supplying 1/3 of the total global steel production. But the main challenge, particularly when you want to make high-performance steels, is the very high content of old scrap, as you can see here. And that fraction of old scrap will grow. And old scrap refers to contaminated and mixed post-consumer scrap. The same applies to the case of aluminum, the second structural alloy mass market, where you see the same trend that we, yes, have an increasing amount of scrap on the market, but the quality of the scrap in terms of chemical composition gets worse and worse. As you can see here from the blue line, which indicates that the majority of the available aluminum scrap is post-consumer scrap. That means it's also chemically highly mixed. And particularly in the world of aluminum alloy production, this is a big challenge. When you think, for instance, of alloys that have a very high silicon content for making cast products, be it engines or gigacastings for electrical vehicles, in contrast to alloys that are meant to be mechanically very strong and tough and contain very high fractions of copper for producing nanoprecipitates, and these alloys are used in planes. When you, however, mix such different alloy streams, you can't use them anymore for either of these applications because the corrosion becomes often really bad and the mechanical properties too. When we leave the area of scrap for the moment and think about the primary minerals that we use in extraction of elements, we have, of course, the big player iron and steel production on the right-hand side. The main point when it comes to the minerals, to the ores that are used here is, for instance, in the case of hematite ore, that it contains up to 70% of iron. That means it's a relatively pure mineral and has only a few percent of gangue of impurity elements. On the other side, when you think of very critical and expensive and CO2-intense alloys or elements such as nickel, or cobalt, but also chromium or rare earth, they often are so-called weathering ores, which contain nowadays only a very small amount below 1.5% of the actual metal that you see. And that makes the enrichment extraction so challenging and also underpins the fact that you are dealing with very high contamination fractions. A third route that we are using in sustainable material science is the so-called tertiary synthesis. This refers to an approach where we use dumped industry waste, such as residues from big industry processes that are on big dumping sites and cost a lot of money, of course, are returned back with extraction methods to reclaim the metals that are often still found in them. Here's one example where we, for instance, were capable to extract the metal content, as shown here, out of red mud, which is a bauxite residue industry waste product from the aluminum industry. When you summarize this along certain main topics, then we understand that we have metals made from mixed ores. That's what we call primary synthesis. But many of these ores are highly contaminated. They are not clean. The second aspect referred to classical recycling, where we have to learn that the quality of the scrap at a global scale has become very poor, and most of the scrap types we have today are also chemically highly mixed. And the same applies to the tertiary synthesis, where we try to reclaim elements from dumped and mixed industry waste. Of course, there are many other strategies that you say, I want to avoid all these other routes and try to replace, using critical elements by inventing simply new materials, like magnets that could work without rare earth elements. And another strategy overlapping with this is, of course, trying to develop new alloys and processes that can cope without the use of critical, strategic, or very costly elements, when you, for instance, think of the world of catalysis. The common notion, however, in all of these first, secondary, and tertiary extraction methods is that it is very, very mixed and highly chemically contaminated material. It means contamination is a joint denominator for all of these challenges. And when you look just at the mixing entropy that is related here for a simple binary case with this contamination, then you can see colored here in blue the mixing entropy function here in arbitrary units, as you see, which is, of course, maximum the more you add in terms of contamination, indicated here in terms of the X, which stands for the contaminant concentration. The main important point of this diagram, however, is the first derivative. That means when you want to chemically clean the material in order to make high-performance alloys from such resources, you have a derivative which goes on both sides towards infinity. That means when you want to clean the materials, you must, at the very high purity end of things, consider a very, very high energy loss when you try to do this. And this is a driving force that suggests to us to invent new types of alloys that can cope with higher scrap fractions in order to stay away from this area where the chemical cleaning is an uphill battle against mixing entropy. Thank you very much for your attention.